All right, we're going to talk about a new topic now that's unrelated to continuations. We're going to talk about the concept of safety. All right, so recall when we talked about errors, we talked about what happens when our program has something in it like 1 divided by 0, or when we try to call the function 5 and give it an argument 3, which of course makes no sense because 5 isn't a function. Okay, so what actually happens inside of our code? So let's look at the function case. Okay, so inside of our theory, we would write a rule like this. It would say something like E applied to UV, where U is not a primitive or a lambda. Then we would go to E abort, and then we would write a message like tried to call non-function. Okay, that would be like an example of what it would say. Okay, but now translating this to our CEK machine, what happens? Well, in our CEK machine, we would have a rule that would look like this. We would say, all right, you've got V, and then there's some environment that we don't care about. Then there's a K app, and there's the first piece of the application would be some U, that means some value. There's an environment we don't care about, then there's nothing else, and then there's a K. And then we would translate this to, for example, abort tried to call non-function. And then there would be, an environment that we don't care about in K. So that would be an example of what we could do, where we have this high-level problem of applying things that are not functions. In the theory, we can write it as a rule like this, and in the CEK machine, we can write it like that. But now, the next thing is, how do we translate that actually really into our C code when we turn this into C code? Well, what's going to happen is that you're going to have a rule that's going to look something like this. You're going to switch on the C, its tag. So on the C part of the CEK machine, you're going to switch on its tag, and then you're going to have a case, that's going to be for whether there's like a code and an if, and so on. And then eventually you're going to get down to the case for when it's a number, and there would be actual code right here. And then there would be a case for like when it's a lambda, lam, and so on. But then there'd be a case for when it's a number, or when it is a bool, and these would all be together. So there would be case number, and then immediately after that, case bool. Because whenever there's a value, then what you'd want to do is now you'd want to switch on the K components tag, and then you might have a case for if it was an if, and there'd be something, and then you're going to have a case for when it's an app. Now, once you know it's an app, what you want to do is you want to figure out whether there's more to evaluate. So you would do something like if, I'll write a function. Well, let's imagine there's a function called isNull, and then we would do the K component, and then we would look at the expressions. And if they're null, then that means that this second part of the K app is nothing. Okay? Then what we might do is we might make a rule that said something like if is primitive, and actually how could we do that? Like what really is this is null and is primitive function here? Let me write them again. What we're really saying is that we're going to look at the K component's e's and look at its tag and see if that's equal to empty. And then we would have a case there that would say, well, let's look at the values and look at the first thing, and then we want to look at its tag, and then we want to see if that is equal to a closure. And we would do something. And if it's not equal to a closure, then we would check to see if it's equal to a primitive. And then we would do something else. And then otherwise what we would do is then we would throw an error. Now, we wouldn't literally throw an error like in the programming language. What we would do is we would like do the abort sequence or the throw sequence, whatever that is. Now, when I say do that, what I mean is that we would do whatever this is. So we would construct an abort object with the appropriate string and so on. And so notice that in our code, we are checking every single situation to make sure that that situation is done properly, meaning that we don't accidentally do the wrong thing. This is called having a safe kernel. A safe kernel. The CK machine is referred to as the kernel of our language. A safe kernel of our language is when the lowest level enforces the invariance of the language. The invariance of the language. And for example, our language has the invariant that you can only apply primitives, lambdas, and continuations. Only those three things. So if you try to apply something else, then it won't work. Okay. Now, it turns out that this is expensive. This is expensive. Now, why is it expensive? It's expensive because doing this test right here to check the tag and make sure it's the right thing is inherently expensive. To check to make sure something is the right kind of thing right before you do it. Now, maybe in the case of closures, like maybe in the case of applications, this is not a problem, but it is a problem if we were to look at something like how the delta function works. So if we look at the delta function, it's going to have a type that's something like this, where it's going to return an object in our language. It's called with delta, and then it's going to have as arguments, it's going to return a pointer to an object, the args, okay, and it's going to look something like this. It's going to have a rule that says something like, actually, let's put something else. So let's imagine we're looking at the code in delta for addition. Okay. The simplest way that we could do that is it would look something like this. We would say, look at the first argument. Then take that argument and then cast it as a number object. Then once you cast it as a number object, then look at the number. And then add that to casting the next one as a number and looking at its thing. And take these things right here and take that and put it inside of make number. Okay? So this would be the simplest thing to do. We always make a number, and what we do is we assume our arguments are actually numbers and then immediately cast them and then pull out their value. Now, this of course is totally wrong if the first argument happened to not be a number. For instance, if we wrote, plus true, false. This code right here would run like true. What it would be is it would be the result of calling like make bool with true, okay? And what that would be is if we looked at its struct, it would probably be something like, struct, and then there'd be a bool t value. That would be like maybe we would call it b, if you're like me. And the thing is that this boolean would be stored in the same place as a number inside of this. So what would happen is that this would then return 1, because if you look at the bits, they actually line up, so it works. But this would not respect the invariance of our language, which is that you can only do addition on actual numbers. And so instead, what we would have to do is we'd have to write this code more laboriously by saying, is arg0 the same type as a number? If it is, then cast in look. Now what we're doing is we're making so that every time we do addition, which is like an extremely common thing in programs, we can't just actually add things. We have to first check to make sure that they're called with 2 arguments. Check to make sure that the first argument is a number. Check to make sure the second argument is a number, and then do it. So that means before even being able to do any numerical operation, we would be doing 3 tests and 3 if statements. Now, basically, programs are made up of lots and lots of really basic arithmetic operations wrapped by all sorts of stuff. And so what we're kind of doing is we're saying that we're going to make it so that every single arithmetic operation is like 4 times as slow, because you still have to pay for the original operation. Now you have to pay, actually it's probably worse than 4 times. You got to pay for the original operation, you got to pay for checking the number of arguments, checking the first one's type, checking the second one's type, okay? And yeah, so it's 4 times as expensive. And that's for every little thing that we do. Like, it would be the same cost for, multiplication, for, looking at the first thing in a pair. All of that would be way, way more expensive. And that is very unfortunate. Okay. It not only is it unfortunate for speed, but it's also going to make it so that it's more difficult to write our CEK machine, because it has all this additional boilerplate. So rather than having a safe kernel language, let me just make a little comment that most languages that you're familiar with, like JavaScript and Python, Ruby, Racket, and so on, they all intend to be safe. Meaning that if we go look at the source code for V8 inside of the JavaScript interpreter, it's not going to say this. Instead, it's going to have those if statements there that I talked about. Similarly, if we go look inside of the Python interpreter, it's going to actually have them and check to make sure that the thing is the right kind of value. In contrast, C is not like this. Nor is C++. So C and C++ don't make any attempt to make sure that the values that you, when you're running your program, that the values that your program claims to be working on are what it's actually working on. So if you write a program in C, you can easily cast a string into a number and then add something to it, and then you'll get totally unpredictable results, because the string as a number will be whatever memory location it happens to be stored in. This is called being unsafe. And what we could do is we could change it so that our CEK machine did this. And if we did that, now our kernel would be unsafe. But although our kernel would be unsafe, that would then mean that our language was unsafe unless we had some barrier between the end user programs and the kernel. And that's what we'll talk about right now. How can we, how to have an unsafe kernel, i.e. fast, and a safe language. The key idea is the following. Imagine that our addition function, right now in our code, so now, there's a plus function, and so plus is the kernel's plus. So when you write a program that uses plus, you're talking about the kernel's plus. Let me change this from now to old. So in the old world, plus would be the kernel's plus. In the new world, plus is in the standard library. And there's something deeper than plus, which we're going to call unsafe dash plus. That is the kernel's plus. Okay? And in Racket, we call this function hash percent plus. Rather than writing unsafe dash plus, we write hash percent plus. Okay, so if unsafe plus is the real plus, how can we use it to implement that plus? Well, what we could do is we could write it in the following way. We would write define plus as taking x and y, and then it would say if and number question mark x number question mark y, then it would do unsafe plus xy, and then otherwise we would call throw, and we would say addition given non-numbers. Close the if, close the define. Now to do this, we would have to add a number question mark function to the kernel, i.e. to the set of primitives. Because so far we didn't have any ability for programs inside of our J language to figure out what kind of thing that they were given. Okay? And we would want to add one of those for every single kind of object in our language. We would want to add a number, We'd want to add box, We'd want to add boolean, We'd want to add pair, We'd want to add unit, We'd want to add in left, in right, continuation, function, okay. We also want to be able to protect against having the wrong number of arguments. So we want to add a function that's called function dash arity, which is going to take a function and tell us how many arguments it takes. See, because although this version of plus right here, this version of plus protects us against calling it with non-numbers, it doesn't protect against a situation like this, where we write plus and we call it with 1, 2, 3 arguments. That is still an error because it's being called with too many arguments. And it would also be an error if we called it with only 1 argument. So how can we deal with that? Well, what we can do is we can add a rule to our desugarer. Our desugarer is going to have the rule that when it gets called with a function and then some arguments, xn, okay? Now this case is whenever, like no other case applies, like f isn't let and etc. Then what we'll do is we'll turn this into the following. We'll turn it into if and function question mark f and equal n function arity f, then it will actually really call the function. Actually, I guess this is really E0 through En. Then it will really call the function. Otherwise, it will call throw. Not a function, not a fun, or wrong arguments. Close the if, okay? Okay. So the idea is that our desugarer now enforces safety by making it so that every time we call one of these anytime we call any function, we check to make sure its arity is right. And in fact, this function thing right here is not quite right. It shouldn't be function ? It should be procedure ? And not function arity, but procedure arity, where procedure would be a function that's like this, that we write in part of our standard library. We would say procedure, x, and it would say, or, is it a function? Or is it a primitive? Or is it a continuation? Because remember, continuations can be applied. Okay? And then there would be another function that would be called define procedure arity. And we would say, if I've been given a function, then return function arity. Otherwise, was I given a primitive, in which case I'll call a function called primitive arity, which I've got to make sure I add to the set of primitives. So there's got to be a function called primitive ? And primitive arity. Okay, primitive and primitive arity. Primitive arity of x. And then otherwise, if it's not a function and it's not a primitive, then that means it must be a continuation, and continuations always have arity 1. So we'll close that, close that, close that. Okay? So the idea here is that we are updating our our standard library to enforce safety so that our underlying CAK machine doesn't, therefore making it so our CAK machine can ultimately be faster. Now, in practice, it won't actually be faster. And the reason it won't actually be faster is because those tests will still be getting done, except that they'll be getting done inside of the language. However, it could potentially be faster because now our C code doesn't have any if statements in it, which means that functions can get inlined better and that we might get better assembly generation. But what is really valuable about this is that now we would have programs in our code that would look something like this. So it would say +1, 2. So this is what our code looked like. And what our desugarer would produce is it would produce something that's like this. It would say if and function, procedure plus, and then procedure arity plus equals 2, close that, then we would call the actual plus function. Otherwise, we would error. Okay. And then inside of that plus function, okay, so hold on. So we would write this code, and our desugarer would return this. Now, imagine in the future we write an optimizer for our language. What an optimizer does is we would take a J program and return a J program that was superior. Well, one of the things that our optimizer could do is it could do what's called constant folding. Basically, the idea of constant folding is that whenever you see a function call and you know which function is being called and what its arguments are, then you can inline it right then and evaluate it at compile time. Which means that we would evaluate this at compile time and it would turn to true, and then this would return to 2, and then 2 equals 2 would return true, and then we would have and true, true, and get true. And then we could have a rule inside of our optimizer that said something like, if you ever write if true x, y, then just turn that directly into x. In which case our optimizer would turn this directly into plus 1, 2. Okay? So that means that our desugarer would add this, and then our optimizer would remove it. So desugarer adds that, and then optimizer would get rid of it. And now the optimizer would have code that was more efficient than before, but it would be guaranteed to be safe. Now another thing that our optimizer is going to do is our optimizer is going to see anytime we have a known function call with known arguments, it can inline it. So it's going to inline this to the following. It's going to inline it to if and number 1, number 2, then it's going to call unsafe plus 1, 2, otherwise it's going to error. Okay, so our optimizer is going to do that, and then our optimizer is going to continue constant folding, and it's going to say, yeah, this is a number, that is a number, and those together. So then it's going to turn it directly into unsafe plus 1, 2. So what our desugarer does is it refactors our implementation so that we still have safety, but rather than the safety being implemented inside of the CEK machine, it's implemented inside of our desugarer, which is kind of like our compiler, and our standard library. And then those cooperate with our optimizer, which can have a very, very small set of simple rules that can be repeatedly applied over and over and over again to derive something like this. So we ultimately would get performance comparable with like C code without having any risk of unsafety. Good languages are implemented like this. Racket's implemented like this, for instance, and good JavaScript interpreters do stuff like this. Python and Ruby are bad languages and they don't do it. They don't work this way. Now, let's go a little bit deeper on an error like this. Throw not a function or wrong argument. What should we want out of an error message? I.e., whenever there is a violation of an invariant, what do we want to know? We would like to know what was sent. We want to know what was supposed to be sent. So let's imagine we wrote code like plus true 3. We want to know what was actually sent, the true. We want to know what was supposed to be sent, a number. We want to know who sent it. And we want to know who received it. Okay? Those are the 4 pieces of information that we would like to know. So who sent it is you, and who received it is plus. Okay. These components right here, okay, so let me step back one moment. There is a basically a rigorous theory about how to write down and talk about safety violations. And this is called the theory of software contracts. So software contracts express and enforce invariants. All right? And they talk about each one of these 4 components. We call this component right here the value. We call this component right here the contract, which we abbreviate as CTC. We call this component the positive label. And we call this one right here the negative label. All right? Now, contracts are enforced by a function called protect. So we write protect, and we write down the contract that we are enforcing, the value that we are protecting, the positive label, and then the negative label. And our desugarer is going to turn this into the following. It's going to turn it into, if the contract is true on the value, then return the value. Otherwise, throw an error that says expected the contract, but got the value at, from the positive label to the negative label. Okay? This protect function is a rigorous way of describing safety violations. So for example, rather than writing our plus function like this, like I talked about, which gives this kind of bad error, what we could do instead is we could change our desugarer so that when we call desugar and we get a plus with two pieces, x and y, what we could do is we could turn this into calling unsafe plus and calling it with protect number question mark x. And then what we could do is we could write down the positive and the negative blame. So maybe what we could do is we can get so our desugarer keeps track of what line each one of these things came from. So maybe this would be like line 27, because maybe that's the line that x is on. And then we know that it's going to plus, because that's the rule for plus. And there would be another call to protect. That would be number y, and maybe this was on line 29, and that would be to plus also. So if we implement the protect function, and our desugarer knows about it, then this is another strategy for providing safety. It is equivalent to the standard library strategy, but what it does is it makes it so we have a more rigorous way of talking about errors. Okay. Now, the thing that is really exciting about this is that it now becomes possible to talk about enforcing contracts that are more than just on basic values. Such contracts are called flat contracts. So 1511, a flat contract is one on an atomic value. For example, number question mark or bool question mark. Those are examples of flat contracts. However, many programs take more interesting contracts than that. So imagine, for instance, we have a function that's called concat map. Okay, and what concat map is going to do is it's going to take a function that goes from a number to a string, and it's also going to take a list of numbers, and then it's going to return a single string, which is the result of calling this function on each one of those numbers and then combining them all together. Okay? We can implement this function in our language, by the way, where if the list is empty, we return the empty string. Otherwise, what we do is we call string append on calling this function on the first thing and recurring on the rest. Now, how could we turn this specification right here into a contract? Well, how could we have a contract on what a list is? So we could say that when you call protect, and you say that you're supposed to be given, let's say, a list of, and then some other contract, CTC, with some value, some positive label, and some negative label, then what that could do is it could call a function. So what it could do is it could basically, recur through, well, first of all, what it would do is it would return like and is this thing a list? Was I given a list? And we can maybe write a function called check all. And what check all would do is we pass the underlying contract and then the value. And hold on, the positive and the negative. And what check all would do, so check all CTC empty positive negative would just be true, okay, because it always works. And when you call check all on the contract and a single thing, let's call it A and D, the positive and the negative, then what that would do is it would do an AND of calling protect on the contract and the A, positive, negative, and then calling itself check all with the contract, the D, the positive, and the negative. And so what this is going to do is when we have a list all, it's going to make sure it's a list, and then it's going to recur through the entire list, checking to make sure that everything is valid. Okay, so that's how we could check to make sure that concat_map was given this thing right here. But how could we make sure that concat_map was actually given a function that took a number and returned a string? In other words, how do you do something like this? How do you protect num arrow string on some arbitrary value x? How do you do that? Well, one thing that you want to do is you want to say something like, and was I really given a procedure? Because maybe you were given a number, okay? And is its arity, procedure arity, is its arity really 1? Because it's supposed to take one argument. But then how do you know that it actually returns a string? Well, what you can do is after you check this thing right here, rather than returning the actual value x, what you do is you return what's called a proxy. So we'll write a function that takes in the argument. Okay, so this is going to take in the argument to x. And what it's going to do is it is going to call the function call x. And it's going to give it the argument. Okay, and then it's going to return that argument. However, it can't just do that, because it needs to make sure that the thing got returned is actually a string. So what we're going to do is we're going to say, let's call protect, and we've got to make sure that it returns the appropriate range. The number is the domain, the string is the range. Okay, we've got to make sure it returns the appropriate range. Okay, and the positive and negative labels are the same. But now, notice that we don't enforce the domain. We're not checking to make sure that argument really is in the right domain. So let's do that. So what we'll do, actually that's not what we want. So what we're going to do is we're going to call protect. Whoops. We're going to call protect with the domain on this argument. Okay. So what this is going to do is it's going to make it so that x is only going to actually receive the argument if it really matches the domain. But now notice that there's a kind of a slight problem here, which is that if there's an error, the positive thing is what it's going to say it's going to be from. But the positive code provided this function x. It didn't provide the argument. Who provided the argument? Well, whoever provided the argument is the person that received this x. And we know that negative received the x. So that means that we actually have to swap these. So we have to put the negative label here and the positive label there, because the negative code is the one that is responsible for constructing this argument value and sending it, And the person who it's being sent to is this positive value right here. Okay, so this right here is called a higher order contract. Higher order contract. It is a way of enforcing, through proxies, contracts on higher order objects like functions. There is a very rich theory of implementing these that I highly recommend that you read about. So if you just Google higher order contract, then you can read about that. These are implemented in JavaScript, Clojure, many languages. They originated in Racket, of course. And with that, that's a good discussion for today of safety and contracts.